All right. So again, moment of inertia of a rectangular a thin plate of a thin plate of anything basically, which has length L and about. So we're going to calculate around about its geometric center, okay, and width W. Okay. So the general formula for the moment of inertia is this: I equals R squared dm integration over all the shape or size of the object. All right. So that's the general formula. And let's take the coordinate system. Let's set the origin at the geometric center of this object. So this is y and this is x. All right. And so again, when you have a situation like this, and on this side you have a situation like this, what we try to do is we try to figure out the dm and also try to so that we can do integration. So in some common variable. So let's say that we have a small mass here that represents our dm. Okay, let's make another assumption that the density of this, the areal density, that it has uniform density. This object has uniform thickness, in other words. Okay, small thickness, not much, because it's simply a sheet, a rectangular sheet, and its density is uniform. By that means that I can write its density as total mass m divided by its area, which is WL. If that is the density, and this little piece is dx and dy, that is the length and width of this little piece, then what would be, can I write dm in terms of dx, dy, and the density? What would be dm then? Density times the area of this little patch here, right? And what is the area of this little patch here?
dx
dx by dy. So rho dx by dy, and then rho is simply m over wl times dx dy. Okay, and let's say that the coordinates, the position where this object is located, is x and y. Okay, so what would be r in terms of x and y? The r or r squared
plus y square.
Yes, or r square, actually better, we have it in the expression x square plus y square. Okay, now we plug these two things in the integral and then try to calculate the integral. Okay,
x square plus y square हो गया, dx square plus dy square होगा.
no, but I'm talking the position from the center. Okay, I'm talking about this r. This is r. Okay,
फिर वो तो सही है, लेकिन अगर हमारे पास जो पॉइंट्स हैं वो dx और dy हैं, तो फिर हमारे पास dx स्क्वायर और dy स्क्वायर नहीं होना चाहिए.
नहीं देखें, रेडियस देखें, एक पॉइंट पार्टिकल है, ठीक है, ये इस डिस्टेंस की बात कर रहे हैं, तो ये तो x और y नहीं होगा. ठीक है, अब इसका अपना इसका अपनी कोई फाइनाइट डायमेंशंस हैं जो dy है और dx है. ठीक है ना, ठीक है, दिस इज x and y, दिस इज द r. So we get r square equals x squared plus y squared, and then we do the integration.
सर आप एक इक्वेशन एक्सप्लेन कर सकते हैं पोजीशन की?
जी जी जी, दोबारा बताएं। हाँ जी, क्या क्या ये बताएं, ये वाली इक्वेशन, ये वाली,
जी सर।
ये आप ये देखें, ये क्या है, पाइथागोरस नहीं है ये चीज मैं कर रहा हूँ, ठीक है। इफ दिस इज x, this is y, then what is r? How is r related to x and y? R square is equal to x squared plus y squared, isn't it? But I think your
ओके थैंक
question,
यू सर।
okay, if this was your question, then good. Um, so what I'm doing is that the motivation really is to find some common variable so that I can do integration. I mean, that otherwise doing this integral in these symbols, in these variables is not easy. So I'm trying to recast the r and dm into actually x and y. And you see, once I'm able to do it, that's the only difficult part in any moment of inertia problem. Okay, integration usually is relatively simple.
So R is the distance from the origin, sir.
Yes. R is the distance from the origin around the point around which I'm trying to calculate the moment of inertia. From the origin of
Okay.
this small mass dm, and uh, and the mass, the dm of this small point, this small patch, is I've written in terms of density times the area of that patch. Okay, and the density, as you
Okay,
can say,
thank you.
mass divided by the area.
Mm.
So the integral then becomes a double integral, and don't worry, it's very simple, because I have two variables, x squared plus y squared. That's the value of r. Then m over wl dx dy. Okay. And then you take all the constants outside, m, wl, and then you just separate the integrals in this way, x squared dx dy plus y squared dx and dy. All right. So the one thing that now we have to figure out here is the limits of integration. Okay, so double variable integration. So the x, if you look here back in the picture, if the origin of the coordinate system is here, and this is my x-axis, then the limits are minus half L by 2 to plus half L. And same is the case with the y. So the limit on y would be half the width minus half the width to plus half the width, because the total width is w and the origin is in the middle. All right. So now these limits, if you introduce
सर हम
here,
दो दफा इंटीग्रेट क्यों कर
G,
हम दो दफा इंटीग्रेट क्यों कर रहे हैं?
because we have two variables, x and y, and we have dx and dy, and we are, or in other words, you can think we have two-dimensional object, x and y, so we have to integrate on both variables.
जी ठीक, थैंक यू.
Okay. So the limit on x would be minus L by 2 to plus L by 2 minus W. And here again, okay. So this is a little bit, okay. So here is what you do. Look at this integral, okay. Whenever you have a situation like this, you can evaluate. First, let's evaluate this integral, okay. Keep the dy integral outside. And what would be this integral?
x cube by 2.
L2 by what would be this L2 by, sorry, L by 2 cube if I also introduce the limits, right? And minus L2 by L by 2 cube over 3. यही होगा ना ये वाला integral, because the integration is x cube by 3, then you introduce the upper limit L by 2 cube minus L by 2 cube over 3. ठीक है ना? And although this integration is now inside this integration over y, but all of these things are constants. So the y integral just comes out here, simple. Minus w by 2 plus w by 2 dy. All right. And I'm just doing the first integral. I'm leaving the second for you. Okay. So this would be here, this integral here. Okay. And then what would be this integral now?
So ये हो जाएगा y हो जाएगा ना dy का तो इंटीग्रल
And limits introduce करें तो क्या हो जाएगा?
w by 2 by plus w by 2 तो ये हो जाएगा w.
Just w. Very good, Shabash. So then, and if I'm, be careful that the cube of minus does not make it a plus. Okay. So this comes out and makes this minus a plus. And then if you simplify this side, you would get outside you have m over wl, and then you have L cube over 12 times W. This would be this integration here, and the integration that I did not do, this integration of y squared, which would be exactly the same. The only difference would be now that the roles of x and y are different. So you would get, you will get W cube over 12 times L. Okay. And then if you simplify, you will get something like this. L squared over 12 plus W squared over 12. Okay, that's it. That's the moment of inertia of a rectangular sheet. Okay, and see if this was not a rectangular sheet but a square sheet, then what would happen? L equals W, and you would get for a square ml square over 6. Okay, this is for rectangle, and this is for a square. All right, any questions? All right, no questions. Then let's do an example. Of rotational motion, all right? So the situation is that we have a uniform rod. Actually, there is a, it should confuse the limits. So we have a uniform rod sitting on two wedges, okay? A and B. All right. Now, at some point, we suddenly pull this wedge out. Okay? We remove it. And this is This is the configuration is horizontal. No other force is acting. We're ignoring friction and all that. So what happens? The rod free falls. This end of the rod falls down, right? Until it hits ground. Falls down. The question that we are trying to answer is, what would be the acceleration? Okay. What would be the acceleration of this end of the rod? That is the question we are trying to answer. Okay.
सर आप प्लीज एक दफा दोबारा क्वेश्चन बता सकते हो? वो मेरा इंटरनेट का इशू था तो आपकी आवाज अटक गई थी.
So again, we have a rod, a rod of a small thin rod sitting on two wedges, and at some point we just remove one of the wedges, okay, and the rod falls down. As it falls down, we want to figure out the acceleration of this end of the rod, okay,
Right.
and the force that is acting on is only gravitational force, all right, and we cannot apply the simple Newton's second law, F is equal to ma, okay, because now we have rotational motion associated with it. It's a rotational motion involved, all right? And what we can do is we can apply the equivalent of this equation that we have for rotational motion. And what is the equivalent of this equation? That is tau equals I alpha, right? Or it has another definition, which is R cross the force. Okay. So now if we can figure out the torque, okay, then we probably be able to figure out, and let's say that the moment of inertia is given, and for a rod like this, the moment of inertia happens to be, and you can, I think we did this this in a lecture before, is 1/3 of ml square. Let's say that L is the length of the rod. Right? So this is moment of inertia. We know moment of inertia. And if we can figure out the torque, we would be able to figure out the rotational acceleration. And if we can figure out the rotational acceleration, then we know that rotational acceleration is related to, or the tangential acceleration is related to the rotational acceleration. So we would be able to answer this question using these equations. All right. The problem with the figuring out torque is that we have gravitational force acting on each point of this rod. So there is force acting here, there is force acting here, there is force acting here. Okay. If there was only single force acting, a contact force at one end or at some point of this rod, it would have been a much easier problem. But we have a gravitational force pulling this rod downwards at every point. And for us to be able to figure out the torque, we start with, again, as we do often, we take a small mass, a small patch of this rod, okay, and this is the point of rotation. This point, this end of the rod stays as it is, okay, does not move, only that end moves. So this is the axis of rotation in a way. So this is the point around which this moves. So let's say that we take a point here, this point here, and let's say that this is its position R, and it has Ri, okay, because there are several points, and the mass of this little patch is Mi, okay. So what would be the torque of this little mass? Wouldn't it be Ri cross the force? And what is the force of gravity on this little mass, Mi? Mgi, sorry, Mij, Mig. All right. So this is the torque on a small piece of this rod. So what would be the total torque if you just sum it for all such pieces? Now see this, mass is a scalar. It's the G that is a vector. So I can just write mass wherever I like in this expression. So MI RI cross G. So, and if you allow me to multiply and divide this thing with M, which is the total mass of the rod. So what is this? Do you recognize? Anyone?
So ये center of mass कुछ लोग कह रहे हैं.
Yes, yes, yes. Center of mass. Yes, yes, yes. So this is the coordinate of the center of mass times G. So you see that apparently it looks an impossible problem to figure out because we have a force acting on every point. It means we should calculate the torque on every point and then add those torques. Actually, when we do that, we come to this very interesting result that if you have a situation like this under gravitational force, you don't really need to, let me just rewrite it more in this fashion. Okay.
सर आप प्लीज एक दफा बता सकते हैं कि आपने उसको कैपिटल एम से क्यों डिवाइड किया हुआ है?
So that this becomes, this is an exact definition of the center of mass. So I plug and then I replace this whole thing with R and then I get MR.
तो सर आपने इसके साथ फिर वो आगे क्योंकि मुझे वो सही क्लियर नहीं नजर आ रहा वो कैपिटल एम मल्टीप्लाई किया हुआ है आपने
हाँ,
कर्ली
हाँ,
ब्रैकेट
sorry, yes, yes. Okay. So now you see this, when you have a situation like this, what happens is that you can take the total mass and calculate the total gravitational force acting on that mass. Okay. And imagine as if that force is acting on the center of mass. Okay. And these two then give you the total torque acting on such an extended object. So you can think of this as if all the mass of this rod is concentrated in its center of mass, okay? And the gravity is acting at that point. When you take the force mg acting on the center of mass, and whatever torque you get would be the torque of the whole rod due to the gravitational force everywhere. So let's write this, let's make this simple. So the direction of the force is downwards, all right? And the R is the distance from the point of rotation to the center of the rod is simply L by 2. And this is mg. So if I only write the z component, and I'm not going to write the z component all the time, let's say that then this equation becomes simply mg times L by 2, a scalar equation. Don't worry about the direction yet. Because the center of mass of such a rod is always at the L by 2. Well, the L is the length of the rod. Is this clear to you, all of you? Most of you?
Yes.
Thank you. Now that means we figured out the torque, which is nothing but mg L by 2. And we also know that torque is equal to I alpha, So we equate these two equations. And on this side, we have I alpha equals mg L by 2. Right? And what is the value of I here? 1/3 of ml squared. Okay, if you plug that value in here and solve this for alpha, what you get is 3/2 g over L. Okay, and now what is the relationship between tangential acceleration and the rotational acceleration? Anyone, please?
A is equals to R alpha.
A is equal to R alpha. Very good. And what is R here? If you remember the figure, or I'll redraw it here. We are interested in the acceleration of this end. So what is R then?
R is L.
R is L. Very good. So A is L alpha. So you bring that value in here, and what do we get then?
3/2 g in the end.
3/2. Okay, remember, this is the value of the acceleration. Okay. Now take a moment and try to rationalize this result. Does it make sense? Is it, first of all, is it intuitive? Is it in line with what we already know?
सर आप
Okay,
प्लीज
so
बता सकते हैं कि वो जो आपके पास I equals to 1/3 ml square है वो आपने किधर से लिया है?
जी जी, ये मोमेंट ऑफ इनर्शिया है इस रॉड का। हमने पीछे एक एग्जांपल की थी 1-2 लेक्चर्स पहले, ठीक है। या अगर नहीं की थी तो यू कैन लुक अप एनी बुक। सो मोमेंट ऑफ इनर्शिया ऑफ ए रॉड of uniform density is always 1/3 of mass times L squared, which is its length, right? And we know, like we know, F is equal to ma, torque is equal to I alpha. Because I've used that equation, and I knew from before. Right? But I want you to focus now on this equation. Look, it should bother you, because what is happening? This end of the rod is falling down freely under the influence of gravity. What should be its acceleration? What acceleration would you have guessed if we hadn't solved this problem?
G.
G. What do we get?
3/2 g.
This is larger than G, right? Larger than, let's do an experiment. If you place a little object here, a little stone up here, and then you remove, what happens?
Falls at G.
The two objects won't fall at the same rate. The end of the rod and that little stone won't fall at the same rate. The little stone would fall, A is equal to G. The end of the rod would fall as 3/2 by G, which is larger, this one. So they would lose contact, and this would fall after, immediately. And you can do this little experiment at home.
तो सर ये क्यों होता है?
Because this rod is not absolutely free. It's a rigid object, and it's attached to this thing, and it is in a rotational motion.
Right.
So it has larger acceleration. It has some very interesting implications, okay? So first of all, again, the physics time and again defies common sense. What you think you know, and you always figure out that there is a surprise waiting for you. All right. Now, what about this? the acceleration of the center of mass. Come on. Now you have the expression. Okay. Now find me the acceleration of the center of mass of this rod.
फिर 3/4 जी हो जाएगी.
3/4g. You just have to plug in, instead of L, you plug in L/2. Okay. And the acceleration of the center of mass would be 3/4g. Now, usually these type of questions, they show up in your exam, so you have to be careful. So can you figure out the point in this rod? If there would be at least one point on this rod which has the acceleration exactly equal to g. Can someone figure that out?
2/3L.
2/3L, very good. So there would be a position x 2/3L. The point at 2/3L will have the exact all right. So if you place the stone at 2/3L, then they would fall together. Or any shorter length, then there would be no free fall, because this would have larger acceleration, the stone, and the rod would have smaller acceleration, so it would just ride on it. But otherwise, in other words, this is the length at which, if you placed the stone on the rightwards, then the stone would lose contact while this happens. And if you place the rod left of this position, then it would just keep riding on it. All right. So something more about this. So again, the rod of mass m, okay, is resting on these two wedges. What is the normal force?
Half mg.
Half mg, yes, because there are 2 points. Very good. It's very simple. Half mg is the normal force. All right. But that is when there is no movement. Now let's figure out what would be the normal force when one end has been removed. So meaning, so at this moment, the normal force on both wedges is exactly half mg, okay, equal to the total weight of the rod. But let's find out the normal force at this end when this wedge has been removed. Okay, and the equation is mg minus n equals ma center of mass, which we just calculated. Now, let's plug in the value of ACM, which is 3/4g. 3/4g. And then if you simplify, solve it for n, please, for me. And what is the answer? Quickly.
सर ये हो जाएगा ना 1/4 mg.
1/4 mg. Very good. Okay. So what was the force when the rod was not falling? What was the normal force on this wedge?
Half mg.
Half mg. And when it is falling down with this, if center of mass is falling with this acceleration, what is the normal force on the left wedge? 1/4 mg. So it has dropped by a half. Okay. Now, well, this is expected because you have it accelerating, but if you want to, I would advise against doing the experiment unless you actually work with those kind of objects for anyway. Let's imagine yourself that you are holding a heavy beam. The people who work on construction sites have this experience, and if you ask them without knowing the physics from experience, they would know the answer or the inconvenience that it causes. Let's say two people holding a heavy beam between them, a very heavy and long beam. Okay. Now the other person decides to release it, to leave it. Okay. So what was the weight? What was the normal force that this person was exerting on this end?
1 by
Half
2
mg.
mg.
1 by 2 mg. But when the other person releases the beam, the other end of the beam, what is the normal force?
1 by 4 mg.
1 by 4 mg. So it feels lighter at this end, although nothing changes. Okay? You feel that you're holding a smaller weight now. It suddenly feels lighter. But what happens when this side hits the ground?
So दूसरी साइड को थोड़ा सा ऊपर आना चाहिए क्योंकि वो ज्यादा फोर्स जो दूसरा वर्कर है इट्स exerting 1 by 2 mg but it needs 1 by 4 तो वो ऊपर आना चाहिए थोड़ा सा rod.
Yes, there would be a reflex action. So you might pull it a little bit further. Yes, that's one thing. But what happens? Yes, that's one thing. Let's ignore that. That's a kind of recoil. But let's ignore that. What happens when it hits the other side on the ground?
Would normal force return to 1 by 2 mg?
Yeah, this is not very simple. You need a small a small calculation to do that. What would be the normal force here? And I'll show you the calculation in a moment. But yes, the answer is right. The force goes from 1 by 4 mg to 1 by half mg suddenly, very suddenly, okay, in time. And this hurts on the person's hands. If you ever done this, or people who work on the construction site, you can ask them. Okay, it becomes lighter. It goes from half mg to 1/4 mg. Then it returns to 1 mg very suddenly, and then you feel a huge pressure on your hand. This person. Okay, so you have to be careful when you're holding something with another person. Do not drop things because the dropping of one end can hurt the other person on the other end. Okay, and if you want to show that this is not straightforward, that this normal force that you need to apply to keep holding this end returns to 1/2 mg, you can just simply do this. Tau is equal to I alpha, and then I is 1/3 ml squared. Okay, and then the gravitational acceleration is, so if you revert the if you reverse the whole equation, then you do and you plug in the alpha, which we calculated, 3 by 2 g over L. So the torque would simplify to half mgl. And if I can write this in terms of the force, FL, then what is the force that you need to keep holding? So here is the point. This is the amount of torque this person needs to keep exerting upwards to counter the torque due to gravity downwards. The other end is on the ground already, okay? So must exert an equal amount of torque, okay? And of course, to exert some torque, this person needs to exert a force upwards. And from here, you can figure out this force turns out to be half mg. Okay, any questions so far?
Sir,
Yes.
shouldn't the force be the same as it was when we had it in free fall? मेरा मतलब है कि when we took out, for example, above जब हमने peg निकाला था जो भी था, the force that was falling at, isn't it going to be the same now since it's just the other side that's falling at free fall as well?
Yes, that's the whole point of this exercise, that it is not the same. The normal force that this person has to exert upwards, or this wedge, it changes in the free fall. Okay, and it's not perfectly free fall, so it's careless. It's a rotation under gravity. Free fall means the acceleration is equal to g. We just learned that it is not. Okay, so it's a rotation, an object rotating under the influence of gravity, and this side, the normal force decreases. And of course, if it is a wedge, can't tell us what if the force has changed. But in a human example, you can tell that actually you feel that.
Sir, ये मेरा मतलब था।
Yes, आपकी आवाज कट गई है।
सर जो मैं बोलना चाह रहा था कि इन फ्री फॉल हमने बोला था ना कि g is greater than the acceleration is greater than g.
Yes.
तो अगर आप in the construction if one side is on the ground now and the other person is going to feel the weight, right, which we said it was going to be half mg,
Yes.
लेकिन shouldn't it be the same amount that we calculated above, जो हमारे आ रहा था हमारा ऊपर 3/2 mg, because it's now the other side is at free fall essentially.
Sorry, I'm not getting your question properly, but let me give you this example again. Let me say it again, and hopefully that's when both people are holding the ends of the beam, both of them are exerting this force upwards. Okay, equal force upwards, half mg. So they are carrying equal weight. Okay? If the beam is uniform, so that it's not thicker on one side, lighter on one side, and heavier on the other side, if it is uniform and they are holding from the extreme edges, then both of them are exerting this much force upwards. When one of the person drops, during the process of fall, the other person has to exert a smaller force to keep his or her end up. Okay, to keep their end up, this person. Okay, when the beam hits the ground, all right, once the beam has hit the ground, has come to rest, this person has to again exert half mg force. It returns. So these are three situations: before the fall, during the fall, and after the fall. Now tell me, what is the confusion? Who was it? Abdur Rahman? Is it okay?
I understand this, लेकिन वो फिर ऊपर वाला ही नहीं समझ आ रहा है कि g, why is g greater when it was falling up? फिर वही आ गया.
Oh, we are talking about this end. Okay, so sorry about that. We're talking about the end that is not moving. All right. Now let me say this about the end that is moving. The end that is moving, its acceleration is 0. Okay, because the normal force is half mg, and together with this normal force, the system is in equilibrium, no movement, nothing is happening. Both ends are exerting exactly this much force upwards to counter the weight, which is mg, and nothing is moving. Once you remove this wedge, then this side accelerates downwards at a is equal to 2/3g, which is larger than g. Okay, it accelerates. Once it hits the ground, the acceleration comes back to 0. No more movement. So that is the situation on this end. During the free fall, no normal force, is only the gravity acting downwards. Before, the normal force is exactly equal to the weight that this side has to carry. And after it hits the ground, again, the normal force is equal to the weight that it must carry, and it stops. Now again, come again, Abdur Rahman.
Okay, sir, I understand.
Okay, thank you, welcome. So we figured out the acceleration, the tangential acceleration. But what about if we are interested in what in the rotational, for example, in the rotational velocity omega, would it be constant while the object is falling, while the rod is falling? Would it be constant?
No.
No, because alpha is it's accelerating. So acceleration is not constant. So acceleration is constant, but the object is accelerating. So the velocity won't be constant as a function of time. So we cannot apply this relationship. We cannot find out omega by simply multiplying alpha with time. Oh no, sorry. The reason is because, or let me just say it in another way, because if you see, this is the rod in this direction, and this is the force. Okay? As this rod falls down, the angle between the force and R or L or the rod itself keeps changing. Okay? If that angle is changing, that means the rotational acceleration alpha keeps changing. Okay? So alpha is no more constant. And if alpha is not constant, then we cannot write omega equal to alpha of t. So now I want to make another important point here. And do you remember when we had the situation where force was position dependent and we said we couldn't solve this equation, right? Because the force was position dependent. So we couldn't know the force without knowing the position, and we couldn't know the position without solving the equation. So what did we do? What was the workaround?
Integrated.
No, we use the work energy theorem. We say let's figure. We developed a new formalism where we didn't have to deal with the force, because force became position dependent. So now let's say. So now we have a torque which is position dependent. The torque is changing as the angle changes. Okay, so position dependent or orientation dependent, you can call it whatever way you like. Okay, so whenever we have a situation where the torque depends on position, and indeed in rotational kinematics or dynamics, theta is our representation of position, right? Equivalent of R. So tau depends on R. And when we have a situation like this, we cannot solve this equation. Because tau depends on theta, and we do not know what theta is. To know theta, we must solve this equation, find the alpha, which is related to omega by this relationship, and then eventually it is related to d square theta over dt. So this is the only way to find theta as a function of time is by solving this equation. And to be able to solve this equation, we must know torque. And to know torque, we must know the angle theta, because now tau depends on theta. It's exactly the same situation we had with forces, force and acceleration, force and position. And whenever we have a situation like this, then in case of force, we were able to write or reformulate the.
Excuse me sir, before you move on, आप please ये दोबारा से मुझे समझा सकते हैं जो आपने बताया कि if it's unknown theta तो फिर क्या होगा?
Okay, बता देता हूँ, ठीक है. So let me just erase all of this. Okay. Do you are you comfortable reading this equation?
Yes.
Now, if you
Yes.
solve this is a differential equation, okay? And if you solve it, to be able to solve this differential equation, first of all, when we solve it for r as a function of time. That is the quantity we would get if we were able to solve this equation. Second point is that to be able to solve this equation, we must know the force beforehand. I said this before in earlier lectures, and I'm saying it again, that Newton's laws of motion do not tell you where this force is coming from. You have to figure this out. The Newton's machinery works once you throw in all the forces correctly and solve this equation, it gives you r as a function of time. But this is our responsibility to figure out the force. Okay, the force could be, for example, the force of gravity. Now we exactly know what is the force. We can solve this equation now. The force could be a spring force. It could be a spring force minus kx. Okay, it can be a numerical force that you are applying by hand, 10 Newton. Okay, but it is our responsibility to know this force. But in nature, in reality, we end up with situations where force depends on the position itself. For example, if you were talking about the force of gravity with some constants here, let's say, the force of gravity depends on r. Okay? It depends on where you are. I mean, this approximation that the acceleration is constant or the force of gravity, that is only true near the surface of Earth. Far away, it is not. For example, the electrostatic force between objects also depends on the position, how far away from the object you are. Right? Once you have this situation, now you do not know the value of force without knowing r. And you cannot know r without solving the equation. You cannot solve the equation without knowing the force again. And you cannot know the force without knowing r. So you see, it's a cyclical problem. Whenever
Right.
you have situations like this, we try to work around and figure out all these quantities without solving the Newton's second law, okay? Without solving this equation. Or we figure out a new equation where we don't have to deal with forces, and it's possible. Okay, that is what work kinetic energy theorem is. Now, what I'm saying is exactly that we have a situation where we have I, the moment of inertia, d squared theta over dt squared. And on this side, we have a torque which depends on theta, has some dependence on theta. The same problem exactly that you have here. Now, this equation, you would always solve it for theta as a function of time. But you can't, because to start with solving this equation, you must know the torque, and torque depends on theta. So you must know theta, and you can't know theta without solving the equation. That is the problem. Okay. Whenever we have a situation like this, and it happens to be the case in this case, that the torque is, what is torque? Torque is, in this case, R cross F. Okay. And R cross F, if you write it in magnitudes, that is RF sine theta, the angle between the two. And as the rod moves down, the angle between the rod and the gravity always remains pointing downwards, is changing. So the torque is now angle dependent. Right? So you cannot solve this equation.
Say.
Okay. So I'm going to just repeat what we just said. So you know that alpha is nothing but the time rate of change of the angular velocity, right? And you can further write this using the chain rule, d omega over d theta over dt. Let me know if you're not comfortable with this manipulation. You can just think of this, that I've multiplied and divided this whole thing, this here, with d theta, and then rearranged things. All right, so what is this then? The quantity in parenthesis?
Omega.
Rate
Omega.
of change of angle.
Yes, and that is omega. So then it becomes I omega d omega over d theta, right? So get this expression. And now I do a little bit of more manipulation, and I bring d theta over here. So, right? And then we integrate on both sides. Tau d theta, and that would be from some theta I to a some theta f equals some omega I to some omega f I omega d omega. Okay. I'm just writing the main relationship that the torque has with the rotational acceleration. Okay. Just this is an integral form of that. I've not done anything new. Now, if you evaluate this integral here, okay, I is a constant, you can take it outside, and the rest of the integration turns out to be half I omega f squared minus half I omega I squared. All right. So at least the right hand side of this equation looks something. Does it look does it look familiar or similar to something that we know of?
तो kinetic energy की तरह लगेगा.
So there's a change in kinetic energy. It looks very similar, but we do not know whether these quantities are kinetic energy. Do we know that? We have the expression for kinetic energy, that is half mv squared. And then the work energy theorem was that the change in the kinetic energy, half mvf times half mvi squared, is equal to the work done. Okay, so we'll talk about the left side, whether this is work or not, after first we need to figure out if is this energy. Do you know the answer? One
Sir,
way or
अगर
the
I
other?
को m r square से multiply करेंगे तो फिर वो kinetic energy की तरह similar हो जाएगा.
Yes, very good. This indeed is kinetic energy. And if you want to see that, you can do this, for example. So this is rotational kinetic energy. It has the same units as the kinetic energy. Okay. And it is expressed in terms of moment of inertia and the angular velocity. Okay. This is the initial rotational kinetic energy. This is the final rotational kinetic energy, and their difference indeed is work. Okay. And you can do a simple calculation. Let's say again that we are talking about a rod and a small mass somewhere sitting on that rod is moving downwards with the velocity v. Okay, then its kinetic energy. Let me just do another. So see this, if, for example, this is the rod, okay, and it is a small mass here is coming down, small mass mi coming down with vi, Okay, what would be its kinetic energy of this little mass? Half mv I, right? And what would be the total kinetic energy if you sum it for all the masses? And then
So ये VI square नहीं होगा kinetic energy के लिए?
yes, V square. Okay. And what is the relationship of V with omega?
R omega, V is equals to R omega.
V is equal to R omega. So if you plug this in here, half mi ri squared omega squared let me just rewrite half sum mi ri omega squared. What is this then? The moment of inertia, no? So half I omega squared. Okay. So this indeed is half I omega square indeed is the kinetic energy. And if these are kinetic energies, then this definitely is work done by the torque. Okay. So we have an equivalent of the work energy theorem for rotational dynamics. The only difference is left side is the same. The work is the work and has the units of energy. The right side, instead of having the linear kinetic energy, you have rotational kinetic energy, which is half m half I omega squared. Okay. Now we would use this to our particular example and try to answer this, try to figure out omega.
Sir, अगर left side को हमने integrate करना हो तो that'll give us torque into theta
That would
or
be give
torque
us
into
what?
change in theta.
You can't integrate because it's a general problem unless you know what the how torque depends on theta.
Okay.
You can't do explicit integration here. All you can do is no, you can't. Without knowing the functional dependence of torque on theta, you can't do this integration.
Okay, thank you.
Okay, let's now do that exactly. Actually, let's find out the, in our case, what is, again, this is the rod. Okay, and its one end is falling. Let's say that it makes angle theta as it falls. It makes angle theta with the horizontal or the starting position. Okay, and then I can simply write the torque in terms of angle mg L by 2 cosine theta. Okay, that would be the torque. Let me know if this is not clear. You see, when the theta is 0, when the rod is in a perfectly horizontal position, the cosine 0 is 1, and then you have maximum torque mg L by 2. And as the angle increases, the torque decreases. And you see when the object is, when the rod is perfectly perpendicular, the torque is 0, as it should be, because now that this is the position of rod and that is the position of the force. So they have become parallel. There would be no torque due to gravity anymore. All right, so this is the torque. Now let's figure out the work done by the torque, and the work done by the torque would be d theta prime mg. And exactly, somebody asked about how to do the integration. That is exactly what we do, what we are doing now, because now we know the explicit expression of the torque. We plug this in here, then we choose the limits. So theta goes from 0 to some value. Okay, can go to 90, but we are trying to do a general expression so that we can plug in the numerical value of theta later on. Okay, so we integrate from 0 to theta. All right. So what is this integral then? Everything else is constant except for cosine theta. So the integral becomes mg L by 2 sine theta. So this is work done by the torque, okay, or the torque due to gravitational force in moving an object or in rotating this rod by angle theta. So you can plug in the value of theta and figure out the maximum amount of work done. So for example, if the theta is 0, what is work done?
0.
0, because it hasn't moved. When theta is 90, what is work done?
mgl by 2.
mgl by 2, maximum work done. Okay. And of course, in between, for the values of the angle in between, you will have in between, you would have work done that is in between this value mgl by 2 and 0. Right.
Sir, can you please explain why it's theta prime? And
All
what does that mean exactly?
it does not mean anything. Let me just say this phi. Okay. Phi. Okay. So let's say that this angle is, we are integrating over phi, and then we choose the limit from 0 to theta. But theta is another variable. Is there any
Okay.
problem with this?
Oh, okay. Thank you.
Theta prime is a different variable. But the logic or the reasoning, you see this in your notes and many books, and you will see this later in your career as well. We very often want to do is that we want to show that we are doing the same thing, but we want the integral, the answer of the integration to be still dependent on theta, okay? The limit, because we defer the choice of, we defer choosing the final limit theta to a later time so that we can plug it. We want to work, we like to work with symbols, not numbers. Okay. Otherwise, I should integrate it to 30, 90, 40, and I'll get a numerical answer, not an expression here. I want to get an expression here. And usually the trick we do is that we take the limit from 0 to a variable theta that we would choose later on. But then the integration becomes confusing if you have theta here as well. Although the two things are related, because this theta is this angle exactly. And what I am saying, this theta is a one definite value of that angle. All right. But I want to keep that definite value as a variable as well, because I want to choose that at a later time. So the trick is that you make this theta prime. Okay. And there was we did this example before, but let me just quickly do it if I have a couple of minutes. See this.
So we can see.
Oh, let's switch the board. See this. Now this is theta. Okay. Any function, anything that you have in the integral, let's say, is this. Okay? Something like this. In this case, it's work, or no, the function is torque. Okay. And the integration tau d theta would give me work. Okay. But this work is poorly defined. All right, because I haven't specified the limits on theta, how much work. Okay, if I define a definite limit from 0 to 30 degrees, then this would be the area under the curve, and then I would know the answer from 0 to 30. I'll get a numerical number. Okay, if I choose the final limit to be 60, I'll get another numerical number here. Okay, so what I want to do is I want to figure out a general answer for omega, which depends on theta. Okay, and I don't want to choose this numerical limit right away. I want to do work from 0 to an undefined limit on theta, upper limit. Okay, so a theta, but then this is my variable x, so I make this theta an auxiliary variable, theta prime. Okay, and this make it a definite value that I would choose later on. And the ulterior motive behind doing this is that we get the area under the curve still a function of theta, the final limit. In this case, for example, the example that we are considering is mgl/2 sine theta, and we can choose theta later on. So this area under the curve, we want to have this relationship. We want the area as a function of the final limit. That's the only thing that you do when you do this trick with theta prime or x prime and then limit taking 0 to x. Okay, then from the work energy theorem, the initial omega I is 0. Okay, and the final velocity is, let's say, omega f. Okay, the final angular velocity. So what would be the change in kinetic energy then? The change in kinetic energy would be half I omega f, and the change in the kinetic energy is equal to the work done. So if you equate these two, this and that expression over there, and then solve it for omega, what do you get? 3g sine theta over L. Okay, this is omega. So we are able to get omega, and then if you further solve, you would be able to get theta as well. And we did not use the common relationship between tau equal to tau and alpha to get here. So we used an equivalent of the work kinetic energy theorem in rotational dynamics. By looking at this, we had another statement about the work energy theorem, that the change in the potential energy or the negative change in the potential energy is equal to work done by the force. So what would be the change in the potential energy in this case?
सर वो भी half omega f के equal ही नहीं होगा I omega f के?
Yes, exactly this amount sine theta, depends on where you stop, to what point. Okay, so that would be the loss in potential energy, and that is exactly the gain in kinetic energy. Okay. I think that's it that I have for today. Okay, thank you very much. And if you have any questions,